Hi, this is Dr. Andrew Chrysler, teaching communication systems. In this series of videos, I'll be using the textbook Modern Digital and Analog Communication Systems, and we'll be discussing topics that can be found within. In these videos, we'll be looking at LTI systems, or Linear Time-Invariant systems. This should be a review of information that you learned in a signals and systems class. So if some of this is not familiar or I'm going too fast, I would encourage you to look in your signals and system book in order to understand this topic better. However, we will be using concepts such as LTI systems in communications, and it's important to have a quick review. So let's begin by looking at this. So a linear time invariant system is often modeled like this. We have a left side with some kind of input side, right? So we have something that goes in, we have something that goes out. We have the system here, which is usually written as a box. We can look at these LTI systems on the top, right? These are time functions. On the bottom, we have frequency functions. We've already developed paths between time and frequency with the Fourier transform, but we now want to think about how systems might handle signals in both time and frequency. So at the output, we have a function, either y of t or y of f, depending on whether you look in the time or frequency domain, where the time domain, right, is based on this convolution, and frequency domain is based on multiplication. So LTI systems, you can characterize these systems equally in time or frequency. So it's equally valid to start with a time domain signal or a frequency domain signal and understand how the whole system works using a transfer function in time or frequency domain. We often use LTI systems to model communication channels. So you've already learned this topic, you've discussed it, thought about systems in the abstract in your signals class, but now let's consider uh, any communication channel to be an LTI system, at least the ones that we're interested in for this class. Additionally, we're only going to consider bounded input, bounded output stable systems. So while such systems exist that are not bounded input, bounded output stable, uh, you can study these in a different class, maybe in a signals class in a more theoretical perspective. But for now, we're just going to consider that our systems do have this form of stability. So stable system properties, so because we're assuming this method of stability, stable systems have this property where the output, y of t, is equal to the transfer function h of t when x of t, this input here, is this impulse function. So this is a special property that we have. So when the input is a impulse function, right, and the impulse function looks something like this, right, where it increases at one point only, right, then we have a output that is just equal to that transfer function. Stable system properties also have a system response that's convolutional in time, right? So we can characterize this output y of t using the convolution of the system transfer function and the input function in time domain. In frequency domain, right, we have the system response as being multiplicative. So the output is in the frequency domain is equal to the frequency domain transfer function multiplied by the frequency domain input. We can write this LTI system, so we can write a transfer function in this polar form, right, where we have a magnitude and an angle. So we have this HF, this absolute value HF, and this angle. And both of these, right, are in the frequency domain. When we write it this way, we consider this part to be the amplitude response. So we consider this to be the amplitude response, and we consider this angle to be the phase response of the system. So we can characterize a system with a transfer function, and the transfer function we can further break down into amplitude response and phase response. Because of all of the things that we learned, right, in the stable system, we should be able to characterize this output in the frequency domain as being the uh, transfer function multiplied by the input. And doing this, we can take this, so we have HF and XF, and using the polar notation that we just learned, we can break this down so that we see the output amplitude and the output phase, and then we have the input amplitude, transfer function amplitude, and then the angles of these. Further breaking this down, we can determine that the amplitude at the output is going to be these two real parts multiplied together. So the output amplitude would be the input amplitude multiplied by the transfer function amplitude, and the output angle is going to be the sum of the input angle and this transfer function angle.